When you pick up a box of Muquano soap or pour milk from a carton, you're interacting with a solid three-dimensional object. It has height, width, and depth. But every one of these containers shares a common origin. Before it was a box, it was a single flat sheet of cardboard. This creates a specific challenge for manufacturers. They don't buy boxes, they buy two-dimensional materials. To avoid wasting cardboard or creating a carton that can't hold the right amount of milk, they have to calculate exactly how that flat surface will eventually take up space. This spatial puzzle scales up from household packaging to massive architecture. Even the Great Pyramid of Giza relies on these same geometric relationships to transform individual faces and edges into a stable, monumental structure. To manage these structures, we look at three specific properties. There are the faces, the flat surfaces that make up the sides, the edges, where those faces meet, and the vertices, the sharp corner points where the edges intersect. To truly understand how these objects function, we must learn to mentally tear them apart, revealing the flat, two-dimensional blueprints that allow them to exist in our three-dimensional world. Imagine taking a common matchbox and carefully slicing it open along its edges. If you pull the sides apart and press them down, the box becomes a flat pattern. This flat layout is what we call a net. It is the precise map a machine or a builder uses to fold a two-dimensional material into a solid shape. Every flat-sided solid has a net. A cube unfolds into 6 identical squares, while a triangular prism, like a tent, breaks down into rectangles and triangles. Depending on which edges you choose to cut, you can often create several different but equally valid nets for the same shape. The net serves as a bridge. It allows us to use two-dimensional measurements to determine the physical requirements of a three-dimensional object. This brings us to surface area. Think of this as the total amount of material, like wrapping paper or paint, needed to cover the entire outside of the solid. To find this number, you simply calculate the area of each individual rectangle or triangle on the net and add them all together. The sum of those parts is your total surface area. However, the math only works if your units match. You cannot calculate area accurately if some measurements are in centimeters and others are in meters. Watch the scale change as we move through dimensions. A line of 100 centimeters is simple, but a square that is 100 centimeters wide and 100 centimeters long contains 10,000 square centimeters. Pop that square into a cube, and you suddenly have 1 million cubic centimeters of volume. Without unifying these units first, your two-dimensional calculations will fail to produce an accurate three-dimensional result. Once that flat net is folded and sealed, the focus shifts from the material on the outside to the empty space created on the inside. This internal space is volume. While surface area measures the wrapper, volume measures the contents, how much water a tank can hold, or how much soap fits in a box. To find the volume of a rectangular shape, we multiply its three dimensions, length times width times height. This gives us a single value representing the total capacity of the solid. It's important to distinguish between the two. Surface area is about the exterior material. Volume is about the interior capacity. By calculating both, we can determine the most efficient way to build a shape that holds exactly what we need it to. We can apply this logic to more complex structures, like a scout tent. This shape combines a rectangular base with a pyramidal roof. Unfolding the tent into a net reveals 9 simple shapes: 1 floor, 4 walls, and 4 triangular roof panels. By calculating the area for each piece and adding them up, we find the scouts need exactly 170 square meters of canvas. Breaking down a large structure into its component flat shapes makes even complex building projects easier to measure and plan. There is also a consistent mathematical pattern that applies to all flat-sided solids, discovered by the mathematician Leonhard Euler. Euler's formula states that if you take the number of faces, add the vertices, and subtract the edges, you will always get a result of 2. Whether it's a simple cube or a complex prism, the relationship remains the same. Understanding the relationship between two-dimensional nets and three-dimensional solids gives us the tools to design the world around us. Once you know how to unfold a shape, you can accurately build, you can paint, and fill any object you encounter.